Hi everyone. So in this video, I'm going to talk about something which is very central to the way performance marketers are working on a day-to-day basis. So the topic is marginal ROAS. So ROAS goals and ROAS targets, meeting those targets is part and parcel of what performance marketers are doing on a daily basis. But what is marginal ROAS? So marginal ROAS is essentially something that is defined as how much returns you will get upon spending the next dollar. So this is the most central definition. It can be derived from calculus. We'll just see in a moment. But beyond just the mathematics, just to understand the basic concept, we can actually look at this curve. This can be considered as revenue curves or saturation curves because we have spend on the x-axis and we have revenue on the y-axis. Revenue as a function of the spend, of course. So you can see that there are three different channels here, and we can basically conceptualize them as having different coefficients and different ROAS. But the most important point is that irrespective of what their overall average ROAS is, it's important at what point the allocation of budget becomes optimal. Beyond that, the marginal ROAS becomes such that it's not possible to profitably add any additional dollar in that channel. So that is the definition of marginal ROAS. This is very crucial. This is the basis. This is on the basis of which actual budgeting and budget allocation decisions should be taken. That's of course not the case always. In fact, very rarely. Because the most important thing is that to even arrive at this, you will actually have to do an analysis like a marketing mix modeling, which is a kind of statistical modeling. So you see here that in this revenue curves, these darker points are essentially the optimal points. And if we come to the graph below that, you'll actually see an even better explanation of this point. You'll see that there's this horizontal dotted line here, somewhere just below 0.75 and above 0.75 and above zero point 0.5. The one that's running through here, which is actually 0.707, equal to a value called lambda, which we'll become familiar with in the next few minutes. This dotted line is basically the m ROAS, the marginal ROAS. And see that under this optimal condition, what's happening is, this is an interesting property. Essentially, that's what I also wanted to talk about in this video. Is that under this optimal allocation of budget, across all channels and without any other additional restrictions, if you have the opportunity to constantly keep reallocating budgets between the channels or among the channels, based on the idea of maximizing revenue, that's your ultimate objective, then comes a point when the marginal ROAS actually converges for all the channels. They sort of become equal, and they become equal to a certain value called lambda, and in this case it's 0.707. We'll come to that, but hope you can understand here. So these are the optimal spend points corresponding to the marginal ROAS for each of these different channels. The marginal ROAS remains the same, but of course the curves are different, which is why you have different levels of spend here. Okay, so that's what these three things correspond to. If I just come to how it has been defined, we'll actually see that a is defined as this is where in fact, what I'll do is I'll first show you the equation. So let's actually look at what this response curve is looking like. What is the relationship like between spend and I'll just show you this equation first. So the relationship is like this. So this is the revenue, and based on the spend of the channels, the it's a very simple equation just for illustration purposes that has been taken. So revenue is a function of the spends of the channels xi, and it has this coefficient alpha I. So that is your essentially revenue by spend will give you ROAS, but alpha I here is your coefficient for this revenue. So uh, that's basically how it has been defined. And root over of xi, that actually is giving the shape of the curve. So if I actually go back to the response curve here, you can see that is that diminishing returns effect, because root over x simply means that it's the power is less than 1, right? So going to, as x is going to increase, it is going to have a diminishing effect. So that is basically how the curve has been defined. The remaining part I'll come to later. So if we actually now go to the start of the mathematical derivation, that will sort of become easier. So what we are going to try to do actually is basically solve what is called a constraint optimization problem. So this is derived from the tradition of mathematical optimization, very old tradition, and we're going to try and solve for maximizing of fx. That is the main mathematical form that we're going to go after. There is a constraint, however. Fx, by the way, again, in this in this context, is going to be the main revenue function, right? Because in our case, if you remember, this is r of x, which has been defined as this constant, rather not this constant, but rather this coefficient and root over of x of I. So basically different channels have their spends, and you have also a of I, which is the different coefficients for each of these channels. So f of x becomes that one. Now you also have a budget constraint, right? So you have a limitation of the budget, that the total amount of budget that it can go across the channels. So g of x becomes another function which must be less than equal to b. So that's essentially like a budget constraint, but this is the general formulation of the mathematical the general mathematical formulation. Now comes something called a Lagrangian. Now this is where that lambda comes into the picture. This is why it's important, and this, the M rows convergence, under this optimal allocation situation, this is where lambda becomes critical. So lambda is nothing but this actually features in this mathematical optimization problem formulation. So this expression here, this is basically L of x lambda, and this you can see is fx plus lambda into b minus gx. So essentially what it is giving us is the way to actually, so essentially if you can define it as like, if you maximize this one on the left hand side and equate it to zero, and you can see that's what we're going to get in the first order conditions. So you try to take del L of del x, so that's your partial derivative, rather, sorry, for for this value here, which stands for the overall revenue, for instance, in our case. That will become that will be equated to zero. So this is basically your local maxima. Okay, that's the definition that comes from calculus. So this is the usual condition, that marginal benefit is lambda into marginal cost. Okay, so solving for this equation gives us the uh, the lambda. So solution for the equation, sorry, not gives us a lambda, but basically gives us the solution for but this particular optimization problem. And lambda, on the other hand, is if the constant is active. So if if the constant is active, which is this gx being less than equal to b, so lambda is defined as del f dot b divided by del of b. So that's essentially your definition of lambda, where f dot b is the optimal objective value as a function of the resource limit b, because you're taking b here within f of x. So that's essentially where you're supplying that constraint value in the numerator. So just to sort of make it easier, what it means is that lambda is telling you how much the optimal objective would improve. Your optimal objective, remember, is to sort of maximize this value, right? L of x lambda. So how much will that improve if you loosen the constraint b by 1 unit? Okay, so how much that change of b, that constant unit, is going to give you, how much of an improvement is that going to bring about in your objective function, your optimal objective. So that is, I know, quite a bit, but this is basically how the mathematical formulation looks like for the optimization problem. So the whole point here is that ultimately budget allocation is nothing but an optimization problem, And if I just go into the specifics of the problem that we are talking about, the response curve that I showed was this one, right? It was of this form, where you had the coefficient alpha I, and you had the root over of the spends of the different channels. So that is how the response curve, or that is how the revenue curve looks like. Now, how do I derive marginal ROAS from it? Marginal ROAS, remember, we just said at during the earlier part of the discussion, that it's the first derivative, right, with respect to xi. And this is what it looks like. If you take a derivative of this, the first derivative, it's x to the power half. The 2 comes down here, and then you have -1. So half minus 1 is x to the power minus half. So simple basic first derivative. You can look up the formula if you're really interested, or if you need a refresher, but pre-basic. So that's your, so we already have the r dot I xi. Now we have the budget constraint. Remember, it's not an unconstrained problem, this is a constraint problem, and this is reality, right? We do have a maximum amount that we can spend over all the channels. So summation of xi over all i's is your b. That's your constraint. Now comes again that Lagrangian, that formulation for the optimization problem with the Lagrangian multiplier lambda. So you have the summation of this revenue here, this revenue function, minus that section which shows us, where we are actually, how much the differential is between the actual budget, um, from the constraint, and then we multiply it by lambda. So this maximizing for this one will actually give us the optimal condition. So that's why we have the first order condition from it. Remember, we said that it's del L del X. So del L del X here gives us this value, where we basically take the first order derivative. We have already taken the derivative of this. Remember, this first part here is nothing but this r dot I xi, right? Or rather, sorry, this is the r I xi, and you simply have the derivative of that, and we already have that value from here, and this is minus lambda, um, right? Because this is minus lambda, because b is a constant, so you basically have only minus lambda from the the second part of this equation. So, and then you equate it to 0, right? That's the maximum minimum definition of calculus, I mean, way of doing things in calculus. So you just equate it to 0 to find the marginal ROAS, essentially. So this is what leads to marginal ROAS. So you have marginal ROAS of xi from here, which is equal to lambda. Okay, so that's the condition. That's the first order condition for it, for the specific point corresponding to that xi to be a marginal value, which is a maximal or optimal allocation of budget. Okay, so that comes from calculus, that comes from definition. Now let's actually do for solve for our individual channels. So what is root over of xi? That comes out to be, if you just if you just take the if you just solve for this equation, that's how it's coming out to be. So xi becomes alpha I by 2 lambda square. This is where it comes from. Okay, and then you use the budget to find lambda, and then you can just plug in those values here, and you get summation of xi um, equals to this, and this is equals to b, right? Remember, that's our budget constraint, and from there we actually solve for lambda. So this is the formulation, summation of ai square half and root over of that by b. So that's from there you actually get your xi as well, because then you can supply back the value in this particular equation. By using these two, we actually can then connect and sort of get rid of lambda from this whole thing, and we can see that this is, xi can be expressed in this format. Budget allocation only in the form of the budget constraint and the relationship with xi only in the form of this aj's here. Okay, so that's basically the closed form allocation. But the important point here is that we want to verify whether or not it's actually getting equal to lambda. Remember, that's what we wanted to actually check, and if we take the MROAS, we actually saw that MROAS AIXI is actually coming out to be lambda indeed. So this is the formulation, like so we knew what is the mathematical requirement. This is the mathematical requirement. The multiplier lambda has this property, with respect to that constraint unit. It has to be with respect to the constraint unit, that is how it is going to be equated. And that is your definition, because if you look at MRO's definition as well, remember this is how it is coming out to be. It is basically your revenue, with respect to del x. So that first derivative that gives you your MROs, and we see that it ultimately converges to lambda. So this is, this convergence to lambda across all channels is simply under this condition that you are continuously allocating budget optimally based on marginal ROAS. So whichever channel has the lower marginal ROAS, I'm sorry, the highest marginal ROAS in every step, you simply allocate the next dollar to it. That is the whole idea, and you don't stop anywhere. Okay, now this is the overall budget constraint. If you have individual channel level constraints as well, this will not work though, right? So that's an important point to remember. Now actually comes that question of unconstrained optimization. So suppose we talked about the situation where the overall budget was B, right? Summation of spends across all channels. What if that was not there, right? This time though, we'll see later, and I'll just explain in a moment. Instead of say maximizing revenue, let's actually go for maximization of profit. I'll just explain in a moment. So if that's the case, how do we define profit? Remember, there's no budget constraint here. So it's nothing but the summation of the difference between the revenues and the spends, right? That's how we get our profits. Again, this is a simplification. Just think for now, these are the only costs that are involved. So maximizing this value is our objective function. So essentially that's our objective, maximizing of the profit. So that's revenue minus spend. There is no xi equal to b, and therefore no lambda also appears. So same response. So remember, lambda is only important whenever there are such constraints. So the response remains the same. This is our response curve. This is how the revenue and spends are related, and the first derivative looks like this. So this is the objective function of the profit, right? So this is what we want to maximize. So ri of xi, the first derivative, or ri of xi, actually looks like this, right? A of root over of xi, and then we have minus xi, and then we go for the first order condition, right? We saw that. So you have to take a derivative of this profit. We, if you want to maximize something, we have to take the first derivative of it and equate to 0, as we just saw. So r dash I xi minus 1 becomes 0, right? So from there, what actually, if you take a derivative of this is what you get, a very simple equation, right? And then from there we actually see that r dash I xi is actually 1. So in this specific case, therefore, that if you keep spending in a channel until its marginal ROAS equals 1, right? If it becomes lesser than 1, this r dash I xi, then there's no point of adding additional dollars. So you don't want to have any you don't want to spend anymore if the marginal ROAS becomes less than 1, right? So that is the simple point. Like, in when there is no constraint whatsoever on the overall budget or any other constraints at all, then simply the marginal ROAS equals to 1. Okay, that's the optimal budget allocation. And think of it, that completely makes sense, right? Because that simply means that you still continue to adding, you continue adding budget, and this is, remember, all the channels are actually converging to that value, right? So this makes complete sense, of course. So under unconstrained optimization, so if we actually solve for xi, let's actually go to that step as well. So this is, remember, this is what we got. R dash I equals to 1. So r dash I was this, so this becomes equals to 1, right? So you solve for that. Now your spend levels become ai by 2 whole square for each of the channels. Okay, so just the coefficient divided by 2 by square, and square of that, and the m ROAS becomes 1 for every channel. So this is the verification part, because this is where we are using our equation, right, specifically, and we are just verifying if it's actually becoming equal to 1 or not, right? So r dash xi was 1, but we also saw that m ROAS is also becoming 1. So for unconstrained profit maximization, it just basically converges to break even. So that's the point. Like, as long as you don't have any constraints, you can continue spending to the point where it's simply just break even. So, but by break even is simply meant that you are actually maximizing the profit under that condition, right? So you are essentially for that break even at that point essentially. So the marginal row simply means that for every additional dollar, you're getting one in return. So you can keep spending up to that point for every channel to maximize the profit, so you're not letting go of any additional revenue at all. So hope this was clear. I know there was bit of confusion. You can actually use this little tiny numeric check as well, where you provide the a values, the different coefficient values. As you can see, this for this different coefficient values and different x values, the m rows values actually become 1 1 1 under this condition where there is no budget constraint. So now the question is, why did I actually go for a profit rather than a revenue maximization in this second example? The reason was simply because if you think of it, when you don't have any constraints, if you don't have any constraints, your basic problem is maximization of RIXI, right? So if you did not have the second part here, because it was profit, you had to deduct the spend part. Since you did not have that, your revenue actually keeps growing because your XI is tending towards infinity, right? Because you can just keep doing it, right? It's you can keep increasing it, and if you keep doing that, then if you look at this formula here, this r dashed xi, this actually becomes zero, right? This tends to zero here because which is marginal ROAS. This actually tends to zero because the denominator is tending towards infinite, right? So there's no finite optimal value in that situation for this specific problem. That's the way, of course, how we have defined our revenue curve. The revenue curves will differ. So the revenue curves, as I said, these are ultimately determined from marketing mix models, which the revenue curves which best describe the distribution of effect, as we call them, like channel effect, the contribution to overall revenue. Based on that, the models are able to determine what is the best form of the saturation of the revenue curve. But in this example, we just wanted to explore the concept of marginal ROAS, and we see that for revenue maximization, it is profit maximization for which we can solve this. Hope this was useful. This was a very mathematical introduction to the concept here. I think this will help you understand marginal ROAS. So we saw marginal ROAS is ultimately a derivative, right? It comes from calculus, because it's two, ratio of two deltas, right? How much, if you change the spend, how much is it going to impact the change in revenue? And how under optimal allocation situation it actually converges to they all become equal essentially. And because we are using the optimization problem, this formulation, it becomes equal to lambda. We just verified that. So if you have any questions, I know this was a lot if you are uninitiated to the mathematical side of things, but I think you should explore it to understand things better and take better decisions. If you have any questions, do let me know in the comments. If you have any other observations as well, I'm glad to hear and have a nice little discussion around this. But thanks for watching. I'll see you in the next one.